So we already discussed some of the definition for the memory size on the assembly language. So these are actually what that we already discussed. So the assembly language, so we must have the label, where we label that we have the mnemonic and operands. So for the you look at the mnemonic and operands, we have the directives. So the directives is the one that we put at the beginning of the code, right? So these are the example of the directive, which are the DB. So DB stands for database, and we end, and P. So we end the program, and N is the we end the whole uh, code. All right. So the directives are different from the instruction. So the directives are the thing that we call from the CPU. So instead that the instruction, so the instruction is within this area. So the instruction is within the area. So the instruction is the code that we ask. We ask the CPU to do something. So the DB is just we call something from the CPU. And then we also have command. So like this one. This is other comments, right? So, actually, for us to make it easy for us to actually note what is actually been done by each of the code that we for every line. So that's the command. So basically, for example, like this one, so we want to assign the value to ds, so mean that we put ax to ds. So we put the command here, assign value to ds. And so on. And then we also discuss about the model directive. So all of this, all right, over here are the directives. So for example, dot model. So and small, we select the memory model, whether it's small, medium, compact, large, or huge, or tiny. So we have the list of size of memory that we want to choose. So what you need to remember that so between each of those, so we have small, medium, compact, large, huge, and tiny. So the difference is that at 64 kilobytes. So for the small one, right? So the data, must be below than 64 kilobyte. And for the medium, the data must fit into 64 kilobyte, but the code, can exceed 64 kilobyte of memory. So is the difference here is between the data and the code. So the code can exceed, but the data must fit. Meaning that can be smaller, alright, or it can be up to 64 kilobytes. So that's the maximum size. So for the small one, both data and code must fit into 64 kilobyte. And for the compact one, the data can exceed, data can exceed 64 kilobyte, but the code cannot exceed. So it must be within 64 kilobytes. For large, both data and code can exceed 64 kilobyte, but no single set of data. So this is a single set of data. So we can have multiple set of data, right? But for each set of that one cannot exceed 64 kilobyte. Okay, and then we have a upgraded size. So we have huge one. So both code and data can exceed 64K, right? And then the data item, it can exceed 64. Okay, so meaning that over here, so it is much larger than large. So that we can have the set of data can exceed 64 kilobyte. Okay, for the model tiny, so we usually use that with compiles in which data encode must fit into 64 kilobyte. Okay, so it is the tiny one is like the small one, except that is usually used for compiles. Okay, so that's the difference between the model of the memory. So these are the directives. Okay, so every line on a assembly language program must correspond to one uh, 86 CPU segment register. Okay, so we must have, okay, you must, if you want to use the CS, so that must be, as we learned before, that must be complement with the PS and SS with the ES. Okay, so over here, if you want to use this segment register, so how do we define that on the assembly language? So we use the directive as well. Okay, so the way we use the directive is we use .code, .data, and .stack. Okay, all right. So for example, over here, so .stack correspond of the stack segment SS, data correspond to the DS, and code correspond to the CS. Okay, so that's the example for that. Okay, so how we can use the segment register. Okay, so when we put .stack, so it marks the beginning of we are going to use that the stack statement, and also corresponds to the other segment as well. Okay, for example here, we put .stack 64 where we want to reserve 64 bytes of memory for the stack. Okay, so we want to use 64 bytes of memory for the stack. So, but if you want to use other segment such as .code, so we write .code. So this is usually follows after we define the memory size. Okay, whether we want to, so memory size is either small, right, large, huge, okay, compact, right. So that's the memory size. Okay, and then this is followed by the data. Okay, by the data. Okay, so the data over here, for example, we have the data segment, right? For example, so we already use type, and then over here we want to use the data. Okay, and also we want to use the code segment as well. Okay, so each of these register statement is actually already divided. So for each special function. Okay, so we already learned when to use the stack. Okay, when we want to use the data, right, and when we want to use the code segment, right. Code segment, we just put the instruction inside that. For the data, so the data where we keep the data set inside that. And then for the stack is we want to run the stack statement. Okay, when we keep each of the instructions one by one, stacking that like a ladder. Right, so that's the purpose of having those segment registers within the assembly language program. Okay, for example here, we focus on the data. So we have, we have data 1, data 2, and sum. Okay, so this is the DB, okay, DB directive. So we use that to allocate memory in bite-sized chunk. Okay, so DB, the defined byte. Okay, so DB is defined by the defined byte. So we can allocate different size of that byte. Okay, for example here, we define byte, the data 1 as a 52. Okay, and data 2, we define byte 29. Okay. Okay, so the data items defined in the data segment will be accessed in the code segment by their label. Okay, so this data is later accessed by giving the instruction. Okay, by giving the instruction. For example, over here, okay, we call back the data. Okay, the data over here. So we want to load the data segment address into the, okay. So this is how we relate the code and the data segment. Okay, so we also look from here. So the data 1 and data 2 is already given the value. Okay, so we have the defined byte. So for data 1, it is 50. And the data 2 is 29. Okay, so sum, and then we have the sum. Sum is not given an initial value, but the storage is set aside for it. So for this one, so like this one, we haven't defined anything for the sum, but we already defined that sum, okay, we will have some storage for it. Let's say you want to do a calculation of summing the data of data. So for example, data 1 and data 2, and then the sum will come into action. Okay, so that's the example of the data segment. Okay, and then once we have the data, okay, the data segment, and then we have the code segment. All right. So the first line is the directive. Okay. Okay. So this one is directive. Now this started from here. Okay. It is the instruction. Okay. So this directive is the program. So the prop is this is the program entry point. Okay. So prop is a procedure. Okay. So this stands for the procedure. Okay. So it's designed to accomplish a specific function. The code segment is organized into several small procedures to make the program more structured. Okay, so every procedure must have a name defined by the prop directive. Okay, we have the prop directive. Okay, this must be end with the NP. Okay, where we end the prop. Okay, so the code inside here are the instruction that we are actually doing it, right? So this is what we code. Okay, so inside the procedure, so there must be some instructions. Okay, so the prop and key statements must have the same level. Okay, so the prop directive can be option. So we have over here, we already have it as far, okay, far or near, right? It can be either far. Okay, and then the OS requires the entry point to the user program to be a far procedure. Okay, so we usually use the far procedure because the OS requires the entry point to the user program using the far procedure. So we use the far procedure. Okay, so before the OS passes control to the program, so it may execute, it assign register values. Okay, so when the program begins executing, only code segment and step segment have the proper values. Okay, DS, okay, values are initialized by the program. Okay, for example here, so we initialize the DS. So we determine how much that we want to put, okay, on this data segment. Okay, compared to what we have the code, all right, and also the stack. Okay, because for the code, it is actually a standard procedure where we just put the instruction inside that. But for the data, we need to initialize because you want to know how much the data that we want. Okay, but for the stack, we just define it that just based on the how many bytes that we want to define, and then the CPU will arrange for us on how the code will be assembled within the stack segment. Okay, because we will call back, okay, we will call back the data that we initialize, okay, inside the instruction. Okay, so inside the instruction, within that code segment. So for example, we have this line over here. We call the physical address of the data. Okay, so we put that, okay, we put that data into the AX. Okay, and then follow on by the next step, what we want to do with the data. Okay, the program, okay, for example here, okay, we have load the data into AX, and then later we load AX into the DS. Okay, we assign that to the DS, and then data 1, okay, our data 1, this 52, okay, we define that into the EL, and data 2, this 29, we put that into the BL. Okay, and then this BL 29 is added to 52. Okay, and then we already have the AL as summation of BL, okay, BL and AL. Okay, and then we want to move this value. Okay, so now we move this value into sum. Okay, because we already assigned the storage to the sum. Okay, we store the result in the sum, and then after that we put the data of policy into AH. Right. So that's the instruction that we gave to the program. Okay, and then over here, after that we put the interrupt. Okay, so when we interrupt, and then we end the procedure, and then later we end the program. Okay, So this is how we want to actually keep the program, all right? So this is basically what we want to do, okay? So we just put the instruction over here, okay? And then we put the data over here, all right? So this is basically what the standard program of the assembly language that we need to do, okay? So like previous one, what we need to do here is we just do the summation, okay? And then the data is taken from here, okay? So that's actually the uh, standard way of coding the assembly language. Okay, so how we want to uh, code, right? So how we want to code that? So we can use MASM, okay, which is the assembler. So before this, we use debug, all right? We use debug. So that one is based on the uh, that one is based on the hex programming. Okay, so that one is just we want to code that. Okay, so that is a simple one that we want to code that to instruct the CPU to do something. All right. So for example language, so we use MASM. For example, we use MASM and link. So we want to create more user interface program. Okay, rather than we just use that for CPU program. So that's why we can also use MASM and link. Okay, so many editors or word processors can be used to create or edit the program and produce an ASCII file. Okay, for example, this one, for the output, so it's just like a text file. So .esm, okay, so that is where we can edit the file, okay, and then we need to have the assemble program, okay, from .asm. So we have the obj, okay, so which is the object, okay, and then we link the program to link, okay, .obj to .ese, okay. So ese is the standard program file. Okay, so that's how we link that, okay, from MASM to the link. Okay, the source file must end .esm, okay, and then the .esm file is assembled by an assembler, okay, like MASM. Okay, so one is put into the assembler, then the assembler will produce an object file that we just saw previously, .obj, okay, and in this file, along with other files useful to the programmer. Okay, so from the obj, we use that for the input to the link program to produce the .exe file, okay, where we can execute that. Okay, so the .exe file can be run, okay, by the microprocessor. Okay, so before we feed the .obj file into link, all syntax errors must be corrected. Fixing these errors will not guarantee that will work as intended, okay, as the program may contain conceptual errors. Okay, so we have from the MASM, which is the editor program, and then it produces file.asm, then goes to the assembler program. So we have the list, okay, my file.lst, and then my file.obj, and then we have my file.crf. Okay, so that's the output from the MASM. Okay, once we have that, we can put that into the link program. So the link program, we can produce the executable file, okay, .exe, okay, and also .map. Okay, so that's how the relationship between MASM and the link program. Okay, for example, we have this one. So we can run the MASM on the DOS version, okay, of the whole PC, right? For example, MASM, okay, we call that C myfile.asm, and then we enter. So MASM stands for micro assembler, okay, micro assembler program, which is developed by the Microsoft. Okay, for example, this one. So when we put the MASM C myfile.asm, so we have the object file name .obj, okay, and then we have the source listing .lst file, okay, and then for the cross reference, so we just enter that. Okay, so we have, for example, this is just example. Okay, so we have, okay, for example, it give you over there is still, so we have this much space, okay, for the file to be created. Okay, and then we don't have any warning, and then 0 severe errors as well. Okay, so this is how we can execute, okay, the MASM, okay, of the .asm file. Okay, and then we also have the page, okay, and title directive. Okay, so the page directive, so that's the printer how the list should be printed. Okay, and then is formatted as page, lines, comma, column. Okay, in default mode, if we don't specify the lines, okay, and then we don't specify the columns, so the output will be 66 lines per page and 80 characters per line. So it will print. Okay, for the standard, you just put dot page, and then we don't put any comment after that. How we want to specify the lines, or we want to specify the column, then it will print you the default. So we have only 66 line per page and also 80 characters. Okay, so that will fit on the paper, okay, that you printed. Okay, so in this example, okay, in this lecture, so for example, we use page, okay, 60. So where we print, okay, 60 lines, okay, and then 132 is the number of characters, okay, that can be printed, okay, for one page. Okay, so the range for the number of lines is 10 to 255, and then for the column, okay, is from 60 to 132. Okay, so that is what is specified, okay, when we put this one. Okay, so we have the column from 60 to 132, and then the line, the number of lines is from 10 to 255. Okay, so when the list is printed, the assembler can print the title of the program on the top of each page. Okay, it is common to put the name of program immediately after the title. Okay, and then a brief description of the function of the program. Okay, so this is what can be printed. Okay, so we can print the title of the program. Okay, and then the text after the title sudo instruction cannot be exceeded 60 ASCII characters because we already defined that it must be only 60 characters per line. Okay, so it must be followed. The MASM produces another optional file. So where we look before that, so which has extension of .crf, like this one. Okay, this one we have .obj, .lst, and .crf. Okay, crf the cross-reference file. Okay, and then an alphabetical list of all symbols enables in the program. Okay, so this is where we put the alphabetical list of the symbol and this is optional. If you want to have that file, we can have it. If you want, if you don't want to have that file, we can just ignore that. Okay. So so the program line numbers in which they are referenced. So the MASM, okay, creates the opcodes, operands, and offset addresses under the .obj file. Okay. So inside the .obj, we have the opcodes, operands, and the offset addresses. The link program produce the ready to run program with the .exe. Okay, and then the link program set up the file so it can be loaded by the OS and executed. Okay. The program can be run at the OS level and using the following command. Okay, so we just whenever we want to run the .exe file, so we just execute by typing the name. Okay, by typing the name. So you can do that in your Windows actually. So if that program has .exe file, okay, so we can just run that by typing the name of the file without typing the .exe. But if we type the .exe, that is also fine. Okay. So when we type this, okay, this is called as the mapping because the OS loads the program into the memory. Okay. So which means that the program is mapped into the physical memory of the PC. Okay, so when there are many segments for code or data, okay, there is a need to see where each is located and how many bytes are used for each. Okay, so this is what we can see inside the .map file. Okay, which gives you the name of the segment, okay, where it starts, where it stops, and its size in the bytes. Okay, so we can download the MASM program from this web page. Okay, and then we're going to so we're going to continue with this MASM. We do the real coding. Okay, we do the real coding of the assembly language in the MASM after your semester break later. Okay, so today I'm just going to give you, in terms of the theoretical on how we can code into the MASM. Okay, so we just follow one by one. Okay, what is the code inside the assembly language, and then how we want to execute, okay, the file of .asm, and then until the .exe, okay, and then what is inside of those .obj, okay, .crf, okay, and then also the link file, right? So that's how the relationship from the program that you make, that you run, okay, from the from the assembly language programming inside the assembler, which is the MASM. So before that, and then after this, you follow that until you can create the program to the .exe. Okay, so that's actually what we have learned, okay, so far in this assembly language in this chapter 2. Okay, so we want to look for more sample program. Okay, for example, we want to run and analyze the program that adds 5 bytes of data and then save the results. Okay, the data should be the following hex numbers. Okay, so we have 35, 12, 15, 1F, and 2B. Okay, so it is already mentioned here. So the data should be this one. Okay, so where we want to put this one? Of course, we need to initialize that into the data segment, right? So we want to initialize that to the data segment. Okay, for example here, okay, we have page. Okay, so page is what we're going to print. Okay, so what is we going to print? So we're going to print only maximum we have the 60 characters, okay, for the column. Okay, so you will look that into the horizontal direction. Okay, so from here to here, from from 1 to 60. Okay, so maximum will be only 60 characters can be fit where you print that. But for the line, we can have up to 132 lines. Okay, so that is seen vertically, right? Okay, for example, so we just put the title. Okay, title. So we have prop 2-1, okay, in the bracket exe. So the purpose is we want to add 5 bytes of data. So we determine our memory size, model, small, and stack. So we also still use 64. Okay, and then we have the comment here. So this is just the comment. Okay, this is after the double comma. All right. So we have this. This is the just comment. So this is also the comment. Okay, if you don't want to put this, is also okay. So because this is just the optional. Okay, so we define the data in. So we define byte as 25, 12, 15, 1F, and 2B. Okay, and then remember that for MASM, we need to put H at the back. Okay, it is not similar like debug. Okay, because debug is already designed in the hex programming. But for the MASM, it is designed in the decimal programming. So you must define the hex number by putting hash at the back. Okay, 25H, 12H, 15H, 1FH, 2BH. Okay, and we define sum. Okay, because we want to add the byte, right? So we sum define byte and we put the question mark over there. Right, and then okay, so we put the code. So we open that with the main procedure var. Okay, and then we end that then with the NP. So we end the procedure with the NP. Okay, as usual, so we have this. So we have this standard code, as I mentioned before. So we just continue. Okay, we just continue after this one. Okay, this is our instructions. Okay, first we set the loop counter as 5. Okay, because we want to add 5 bytes of data, okay, and then save the result. Okay, and then first we do the offset data in. Okay, we set the data pointer for the bx. So the data in is from here. Okay, so which is we already initialized. Okay, so we put that into the bx, and then we initialize al, and then we call, okay, the address of bx. Okay, and then we put that into the al. And then, okay, so because the entire program is in the textbook, so after this, what we do is we increment, okay, we increment input I and C bx. Okay, we increment this bx 1 by 1. Okay, so until 5 times. Okay, because we want to add that into the 5 bytes of data, so we run that for 5 times. Okay, and then after that we increment bx. So as you can see, bx increase and then cx will reduce, so we need to decrease cx. Okay, first it runs, okay, with cx equals to 5, and then again after that cx is decreased after we run for the first time, so cx now becomes 0.4, and then run again until we see this decrement cx again, and then it will be 0.3 and follow 0.2, 0.1. Okay, 0.1 is the last one, and then this is become 0. Okay, once it becomes 0, so we don't have any more cx. So when we don't have any more cx, so this loop will stop. Okay, so how do we want to run that again and again? So as before this, we need to put the instruction of jump. Okay, so jump and z, so j and z, jump not 0. So we put that code. Okay, so for that, so we have, after that we sum that, so we sum that al. So from al, for this one, okay, first we have 0. Okay, so al we put into the sum. Sorry, we have bx, okay, because now al is the content of the bx. Now the al, we have that content of bx. Okay, so because we just add 1 by 1 until 5 times, and then later, so we have the instruction of so after this decrement, and then we put the, as I said before, we have jump not 0, jump not 0 as again. So because you can put the code again over here, right? And then we have move instruction. So we have move sum al. Okay, and then as usual, this is repeated again and again and again until cx is 0, and then we do the move, okay, this al into the sum. So now the sum contains the value of what has been added. Okay. Okay, so once we have that, right, so we just follow what has been used before. So we put the move AH for C. Okay, and then we put the interrupt. After that, interrupt 21H, and then we end P, and then we also end the main program. Okay, so end main. Okay, so that is our program. Okay, for adding 5 bytes of data. Okay, we can also check this in the debug as well. Okay. Okay, so from the debug, then okay, so in the debug, we can put the command of U. Okay, we want to unassemble the code. Okay, and then D, we can dump the content. A and G, go to the program or run the program. Okay, so we can just start the program by typing debug and then the name of program. So the name of program is proc2-1.exe. So and then we can type U. Okay, we type U. We want to unassemble the code. Okay, from the code segment of 0 for 19 bytes. Okay, so it will list out. So unassemble will list out what we have done. Okay, and then let's say we want to dump content, then we can type the dump. Okay, for example, we want to put the content at 1066. Okay, double dot 0. So we can put the content over there, and then we go to G. Okay, then we go to G. So we run the program. Okay, so that's how we can link, okay, the assemble language in the MASM and also the debug programming. So the debug programming, we can actually modify the program. Okay, so we can manipulate that by dumping a new code into that. Okay, so let's take a break, okay, for 10 minutes, okay, before we continue. Any questions so far?
No, okay.
Yes, Ambo? No question, all right. Okay, so let's take a break for 10 minutes. So we will continue after this. Okay, let's continue. So basically that program, 2.1 can also be written in different way. Okay, so let's look on how we can rewrite that in different way. This is what I just explained before. So we move the 05 and then we have the data in, the X, increment the X, increment CX. So you can read this. Good. So this is in your notes. Okay. Right. So this is the way that we can write the program 2.1. Okay. So before that, we put all of those data into data in, right? But we can also define that into multiple set of data. Say we have the data 1 to data 5. Okay, so we define each of those data. So this is actually we require more steps, okay, but it is more clear, right? So we can define each of those five. And actually, I like this type of program compared to the first one because it is easier for you to check. Okay, it is easier for you to check at which line if you have error, so you can trace that. Okay, rather than you put all together the data and then you just dump. Okay, you just dump that into a single code. So the difference is that once you have the data from data 1, 2, 3, till 5, and then your code segment will be different. Okay, so what you need to put into your code, so first data, so you add into AL, and then data 1 you put into AL, and then data 2 you put into AL, put all of that into AL. So that will be the summation all of that. Okay, and then lastly you just put AL into the sum. Okay, this is much more easier, right? So before that you need to use the counter, right? So counter, you need to increment and decrement. You need to increase and decrease counter. And then from here, you just add all of the data into AL, and later you just add the AL into the sum data segment. Okay. So that's the two ways you can write the program 2.1. Okay, so we also have program of 2.2-2 as well. Okay, what we need to do here, we need to write and run a program that adds 4 words of data, okay, and then save the result. And then the values will be 234D, 1DE6, 3BCH, 3BC7, okay, 566A. Okay, so that the forwards of data, okay, that we need to add all of that. Okay, so we have 4, and then use debug to verify the sum is 364. Okay, so we need to verify whether the sum is 364, DC 364 or not. Okay, so how do we do that? Okay, so it is similar like what we did before. So because it is similar programming, so we just add the data. So we can create the counter, okay, and then we can decrease that counter, and it adds until all of that 4 data is added, and then we can verify the. Okay, so as usual, so we have the title. Okay, so the title is defined, okay, and then we have the page, okay, is defined. Okay, this is standard one. Okay, model, stack, so comment, so that is standardly defined, and data. Okay, so this is what we need to look. Okay, so over here, so before that, we define byte. Okay, we define byte. But now, okay, over here, we use DW. All right, so we use the DW. Okay, why we need to use the DW? Okay, because this one actually contains uh, a bigger set of data, right? So that's why we define that as DW. Okay, so we set this at the data in, and then we put the DW, and then we put the ORG. Okay, so ORG is also a directive. Okay, so why we use ORG over here? Because in the previous program, so the ORG is not used. So the assembler start at 000, okay, and use the memory for each the data item. Okay, so when we put the ORG, it can use to set the offset address. Okay, so we can use that to set the offset address for the data item. Okay, for example over here, we use the ORG. Okay, so we need to store that at the location of DS, okay, 10. Okay, at DS 10. So we need DS 0, 0, 1, 0. Okay. Okay, so we have here DW. So we define word over here. So DW is for define word. Because now it is a word. Because we have a 16 byte of data. Alright, of course, our sum will also be in terms of DW, and as usual, we put the question mark over there. Okay, and then this is common one, and then this is also common one, and then that is also common one. Okay, so we need to look at the instruction. So for the instruction, so we put AX into DS, okay, and then CX04. So this is also the common one. Okay, we start from here. So where we have the, okay, first we offset the data in. So we put that into the DI. Okay, and then next we initialize BX. Okay, so because it is 4 times, so later we need to add. Okay, we need to add dot di into bx. So we initialize bx. All right, and then after this, so the program will keep adding. Okay, we'll keep adding that content. So over here, so what we have, we add dash LP. Okay, we have add dash LP, so LP, and then double comma, and then we have add bx. Okay, so we add di into the bx. Okay, and then we increment that. So we increment that di. Okay, so which is data in. So we increment that to the point to the next word. So we add that inc di, and then we do second increment inc di as well. Okay, so why we need to increment di to 2? Because the operand that we access is a word. Okay, so a word is 2 bytes. Okay, so that's why we need to increment that di both. So 2 times. Okay, then it will be equivalent to a word. All right, so once we increment that, okay, so we have to decrement the cx. Okay, so once we add the word, okay, so we increment 2 times, but before this we just increment the byte because it is not a word. Okay, it is just a byte. Okay, that byte is just 8 bit of data. Okay, so we just put 1 time of increment. So for the word we need to put 2 times of increment. So this can also be replaced if we don't want to use this. Okay, if we don't want to use this, okay, so we can either use that add di 2. Okay, so we add just 2. So we just put 1 comment. Okay, so once after this, what we need to do is we decrement. Once we do the increment, so we do the decrement, we decrease cx. Okay, so cx initially is 4, and then once we decrease, it becomes 3, and then loop again, becomes 3, and then loop again, becomes 2, and loops again, becomes 1, and loop again, becomes 0, and then it will stop. Okay, because we put the instruction of jump, not 0. So we decrease cx, and then we put a jump, not 0, g and z. So g and z is this one. Okay, sorry, j and z, this one, at lp. Okay, g and z at lp. All right, so that's j and z. Okay, after that, so we put the move si. So as usual, as before this, so we move si. Offset sum. Okay, offset sum. Right, so you get it. Okay, so now you have offset sum. So sum now is added to si. Okay, so what else that we need to do? And then we put the bx into the address of si. Okay, we put the address BX into the address of SI, and then move 4C into AH and interrupt 21. So that's the standard code. And then NP again and main program. So you just follow after that. Okay, so the instruction after this is move SI. So this is the address of SI, the BX. Okay, so that's how we do to add the 4 words of data. Okay, 4 words of data. So a word is 16 byte of data. Okay. So before this, we need to add 5 bytes of data. So bytes is a 4-bit of data. For word, it is 16-bit of data. Okay, so we can also check with the debug. Okay. You can also check with the debug. So how to do that? So we type debug and then the program C double dot and then the name of the program, which is what we define over there. It is prop2-2. Okay, prop2-2.exe, and then we run that. Okay. So we just type. Okay. Whatever word that we want to put there. Okay, we can type U, D, and also G. So like before, like program 2.1. Okay, so that is for the program 2-2. Okay, maybe you a little bit confusing on how to use this program because it is not yet being practiced. Okay, so we will do the real programming. Okay, we will do the real programming after your semester break. Okay, so we will go together after that. Okay, and then you can try out yourself as well. I will give you the whole code. Okay, I will give you the whole code because the code is in the book. All right. So for program 2.1 and also 2.2. Okay, this is what I already mentioned. Okay, so you can look at the notes. Okay, so lastly, okay, before we stop, let's look for the program 2-3. Okay, so what we need to do here, we need to write and run a program that transfers 6 bytes of data from memory locations with offset of 0010 to memory location of offset 0028. Okay, so we want to transfer that. We want to transfer 6 bytes of data. Okay, so we don't give any values over here. So we need to specify ourselves what is that 6 bytes of data. So remember that 6 bytes, one byte if is a 8-bit data, so we only have 2 numbers, right? So like this one, so we define our data. So this is normal. So this is the common one, common and also common. So okay. So we put organize because we want to start at offset of 10. Okay. So if we don't put that, it is also okay. So we want to set it from 10 and then we put dB. Okay. Now it's back to dB because we define the byte because it's just two hex numbers, which is the 8-bit data. Okay, and then we start do the copy. So before this, it is sum. Okay, now we use the copy. So we copy dB. So we start this at the offset address of 28. Okay, and then we type it as 6, okay, because we have 6, okay, byte of data to be transferred, okay, and we type DUP, okay, DUP, and then in the bracket we put the question mark. Okay, so we continue here. So what we have over here, so this is the same one, and also the same one. Okay, so offset data in, so move SI, so as usual, and then offset copy, okay, we put into the DI, okay, and then we move 6 into the CX because we want to decrease the counter later, okay, and then we put the SI, okay, SI, the address, into AL, okay, and then we move, okay, this is AL, we move now, so because now the content of AIs, AL have the SI, then this AL, now we move to the DI. Okay, so we continue this. So this is the loop. All right, we continue this. So what we have, so we increment SI. So once, so this is just a moving. So moving the data. So we move SI, we want to move SI into DI. So we move that SI into DI, into DI. So we use the general purpose register between that SI and DI. So you move that SI into AL first, and then later AL into the DI. So we need to do that for 6 data. Okay, so this is continue for 6 data. So after that, what we need to do is do the increment of the loop. So we increase SI. So SI only 1, and then we increment. So SI, we put INC, SI, and then we also increase DI, INC, DI, and then we decrease CX. Okay, so CX you want to reduce, we decrease CX, and then of course we stop that, okay, with jump not 0, GNZ, and then move loop. Okay, so this one, okay, move loop. Okay, so as usual, below that, so we have move OC, AH, and then we have interrupt 21, and then NP and main. Okay, and then we can check that if we have already transferred the data using the debug. Okay, so that's about program 2-3. Okay, so you can look at here. So this is step-by-step instruction, what is done. Okay. All right, so that's it for today. Any questions so far? So the content today is a little bit heavy, okay, because you need to think of on how the assembly program works in the MASM, okay, and then you can link that with the debug, okay, to check whether what you did in the MASM is already been done correctly by the MASM. Okay, what has been done? Okay, what is done in the MASM been done correctly by the MASM in the debug programming. Okay, so if there is no question, so let's turn on your camera for today. So remember that we have our test 1 on Thursday. So that will consist of chapter 1 and chapter 2. So I have given you the sets of questions, okay, that you can test, that you can try yourself, okay, with the answers already given, okay, on the WhatsApp group. Okay, guys, turn on your camera. So let's take picture for today's attendance. Okay, I'm gonna count from 10. All right. Cheers, everyone. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. Give me one more shot. Okay. Thank you, everyone. Okay. Selamat berbuka. All right. So remember, so please study for your test 1. That will be on Thursday. Okay. At 4 to 5 p.m. If you have any concern or you have any question, let me know. Okay. Anyway, Assalamualaikum and bye-bye.
Thank you, Doctor.
Thank you,
Thank you,
Doctor.
Doctor.
You're welcome.
Thank you, Doctor.
Welcome.